Thank you so much for coming. This is our fourth lecture of neutrinos, detector, and discovery. I'm really excited for this one. This is all about neutrinos from outer space, which is a great topic just because there's so much, fixing the audio. Okay, there's so much to learn and so much cool stuff that we can do with neutrinos. So I'm going to start off this talk with just a little bit about distance. So distance is going to be pretty important for this talk, so just to get a sense of the scale of different things we'll be talking about. So first, the Earth. In common units that we're going to use throughout this, the Earth is about 10 to the minus 9 light years across. Maybe not so useful for the things we're doing every day, but for this talk, light years will be kind of the unit that we're working in. So to give another sense of scale, another common one is that the sun is about 8 light minutes from Earth. So that means that light from the sun takes about 8 minutes to reach Earth. Zooming out a little bit further, this is just a picture of our sun within our solar system. So about 8 light minutes here. If we want to go even further out, the next closest star that we see light from is Alpha Proxima Centauri system. So a binary star system about 4 light years away. So that means it takes light 4 years to reach us from that system. Anything that happens on those systems, therefore, we won't know about it for approximately 4 years. At the next scale, we have the stars that we see typically in constellations. So Betelgeuse is a famous one, part of the Orion constellation. That's about 700 light years away. So again, if something were to happen on Betelgeuse, we wouldn't know about it for 700 years. But of course, things get a lot bigger, and our solar system, Betelgeuse, all these constellations, those are all part of our Milky Way galaxy. And the Milky Way galaxy is pretty enormous. So we are about 25,000 light years out from the center on this arm called the Sagittarius arm here. And at the center of our galaxy, we believe there's a supermassive black hole that all of this matter and dust and suns are rotating around. But it doesn't even stop there, because outside the Milky Way, of course, we can ask about other galaxies. And those other galaxies are orders of millions or even billions of light years away from us. So the Milky Way, shown here, our next closest galaxy neighbor is Andromeda, 2.5 million light years away. So just having all of this in mind, let's talk about how we detect neutrinos from these different sources. So neutrinos, just a quick review. So 3 important things to know about neutrinos. The first one is that they're electrically neutral. And this has pretty big implications for how we detect them and how we measure them. So because they're electrically neutral, they only interact very weakly. They don't interact very often, and therefore to have a neutrino measurement, you need either a lot of neutrinos to give yourself a really good chance of seeing one, or a really big detector for the same reason. The other thing to know is that they're abundant, so they're produced basically everywhere from every process that does something nuclear. So this is fusion processes in the sun, the sky, where particles are smashing into our atmosphere and producing particle showers. Nuclear reactors, we can make them here at home. And last week we talked about neutrino beams also as another place for these. And then last week we also mentioned that they change flavors. So they have this weird property where they have a tiny bit of mass, and that tiny bit of mass leads to the neutrinos oscillating between different flavors. And by flavor, I mean either the electron flavor, the muon flavor, or the tau flavor. So all of these properties make neutrinos really unique. So starting here at home, close to home, I'm going to talk about neutrinos from our solar system. So the story of neutrinos from the sun is pretty old at this point. So by the mid-1930s, we had already had Pauli propose that the neutrino was a new particle based on observations of beta decay. And also by the mid-1930s, Fermi had proposed a theory that explained beta decay. So physicists were really eager to put all of these things together and start asking questions about other processes throughout the universe. So in particular, this is Hans Bethe. Hans Bethe applied Fermi's theory to the question of energy projection in stars. So he realized that if the sun is doing these nuclear processes like fusion, then you should have neutrino production as well. So Hans Bethe took Fermi's theory before the neutrino was even discovered and applied it to stars. And what he found was that there are 2 main processes in stars that convert hydrogen into helium, which is powering how these stars work. So the first one is the proton-proton chain, where 2 protons fuse together and make deuterium. And in that process, they release a positron and also a neutrino, an electron-flavored neutrino. The other process is a little bit more complicated. It's called the CNO cycle, and what it means is that we have elements of different atomic number, so carbon, nitrogen, and oxygen, and they're constantly being fused with protons and emitting radiation, but ultimately, at the end of the day, you get back to where you started with carbon-12. So if you start with some carbon-12, some fusion process happens, it becomes nitrogen-13, so on and so forth, until you get to nitrogen-15, at which point you emit an alpha particle and get back to carbon-12. And this forms a cycle that produces helium and also could be responsible for powering the sun. Now, this paper that Hans Bethe wrote, he also made quite a bold claim for 1930s, which is that this boron-8 nucleus that he identified as one of the byproducts of these nuclear reactions is not very important for astrophysics. So we'll see how that goes. But I think if you remember from lecture 2, we actually learned a lot from the boron-8 neutrinos. So just a quick review about lecture 2, which is where we talked about the solar neutrino problem. So there was this experiment done by John Bacall and Ray Davis, where they took a giant tank of chlorine, put it very deep underground, and watched to see if solar neutrinos would transform any of that chlorine into argon. And then the two scientists would then go and count the argon and see if they could predict or measure the solar neutrino rate from this. So here's a picture of Ray Davis and John Bacall at the experiment in 1967. And then here's another photo of what it looked like, this walkway spanning across the giant tank of chlorine. And this was the reaction they were looking at. 37 chlorine plus an electron neutrino should make some argon. And so the idea of this experiment is that you're looking for just a few atoms of argon in your giant tank of chlorine. And it sounds very hard, but as Ray Davis was a chemist, he wasn't really intimidated by this. So he did the experiment, and then he kept doing the experiment for years and years. And what was eventually discovered was what we now know as the solar neutrino problem. So this is a plot showing the measurement of the argon-37 produced in this tank over time. And as you can see, the average measurement of this is somewhere around here, but the predictions of what the solar neutrino rate should have been were about 3 times higher. So this was a big question, why this happened. Now, fortunately, Professor Bethe redeems himself 50 years later. He writes another paper, possible explanation for the solar neutrino puzzle. And what Bethe did in this paper was he was building on the work of 3 physicists, Lincoln Wolfenstein, Stanislav Mikheyev, and Alexei Smirnov, who had built a theory about how neutrinos could change flavor in matter. So what he says in the abstract here is that Mikheyev and Smirnov have shown that the electron neutrinos above a certain minimum energy may all be converted into muon neutrinos on their way out through the sun. So what this is essentially saying is that the electron neutrino that is produced in solar fusion reactions, actually a better model of it is something like this. So instead of just a neutrino that's a pure electron neutrino flavor, maybe only part of it is nu E, but some of it gets converted into other flavors. And so that when you detect them on Earth, only a third of them have a chance of being observed as electron neutrino. Now this all came to a head when the SNOW experiment, taking data throughout the late 90s and then into 2000s, released an analysis where they looked at solar neutrino data with 2 separate processes. So this plot shows what SNOW measured, and the 2 colored bands here are showing the different processes they measured. So the first process they only looked at, they looked at a process that was predicted to only happen if you had electron neutrinos. And what they found was that compared to the standard solar model of John Bacall, that rate was about 1/3. So how to read this plot, the horizontal axis here is the boron-8 flux if it was all entirely electron neutrinos. And what they measured was this red band here, so it's about 1/3 of what you would expect if the flux of solar neutrinos were all boron-8. But then their trick was that they had a second process that was sensitive to all neutrino flavors. And that's shown by this purple band. So you can't tell what flavor the neutrino is, but you do know that you measure all the neutrinos regardless of their flavor. And so that was the trick. They measured both an electron neutrino process and a flavor independent process. And they showed that when you account for all the neutrinos, regardless of the flavor, you actually agree with the prediction of the standard solar model. So this dash box here. So this plot over here is showing what the kind of summary of what SNOW published. So this was great. This was a resolution to the solar neutrino problem. they showed that a model where neutrinos had about 1/3 electron-neutrino component could explain the deficit. So there were some questions from both last week's lecture and this morning about how do solar neutrinos change flavor. So last week I talked about oscillations that we do on Earth, and I wanted to go back to revisit solar neutrinos with that kind of concept in mind, but also point out that solar neutrinos change flavor through a slightly different mechanism than what we do on Earth. So the key here is that the difference is density. So I have this diagram here showing the Earth. If you have a neutrino that's produced in the atmosphere, then the density of the material that the neutrino is traveling through is about 0. So there's essentially no matter that that neutrino is going to interact with. So that doesn't mean that there's nothing there. So there's nuclei in the atmosphere that charged particles can interact with just fine, but neutrinos, they have a very low chance of interacting. The effective density that the neutrino sees is about 0. Last week we talked about neutrino beams, and those beams, we aim them through the Earth to go at hundreds of kilometer distances so that we can observe these oscillation effects. But even there, the density is only a little bit higher, so 3 grams per centimeter. So really the corrections that you would have to make to account for neutrinos passing through matter are still small. But when you get to the sun, this is not true anymore. So a neutrino that's produced in the core of the sun has a density, or experiences a density of about 150 grams per centimeter, so much higher than what we experience here on Earth. And this has an effect that we call the matter effect. So the basic idea here is that matter is filled with electrons, and the electrons create what you can think of as a drag on the neutrino as it travels through. So the neutrino is not interacting with these electrons, but these electrons create kind of a potential that the neutrinos experience. Another good analogy is thinking about neutrinos, thinking about light entering a different medium. So as light travels from air to water, it refracts a little bit. So the same effect happens here with neutrinos. The neutrino doesn't slow down, but there's kind of an effective drag. And that drag is due to the electrons. And since the neutrinos have different flavors, only the electron component of this neutrino is affected. So really, the model is that these electrons are constantly putting a little bit of a drag on the electron flavor only, and that changes the effective mass of the neutrino as it travels through matter. Going back a little bit to what we talked about last time with neutrino oscillations, we can think about neutrinos as a superposition of masses. So in this diagram here, we have an electron neutrino, and last time we showed that you could write this as a sum of 2 masses, which we call nu1 and nu2. And the analogy here was that these masses are kind of like clocks. So the clocks are oscillating or rotating at different speeds, and that creates an interference pattern that leads to the flavor change that we know about from oscillations. So if these clocks have different wavelengths or different masses, then you get this interference pattern, and you only have a true electron-neutrino state some of the time. The other part of the time, it's in some in-between state or a different flavor completely. But the effect of this of matter on these masses actually has kind of an interesting implication. So in the vacuum case, it's the picture like I showed before. The electron neutrino can be thought of as a superposition of these masses, nu1 and nu2. And these masses, because there's an equal superposition of them approximately, they're interfering with each other. But in matter, something interesting happens, which is that the electron neutrino is much more likely to be found in the heavier of the 2 mass states. So I'm drawing this diagram here with nu-e shown as a very small nu1 plus a very large nu2. I'm not talking about the masses of these things. I'm talking about the probability of finding a nu-e as a nu1 or as a nu2. And this effect, this change in the relative probability of finding this nu-e state is based on the matter effect. And what happens when you have a very high probability of a nu2 versus a nu1 is that you don't get interference anymore, because this nu1 state is not in equal superposition. It's very much suppressed. So really, the neutrino is propagating as if it were just a nu2 state, the more massive of these 2 states. Okay, so that's kind of the overview of how solar neutrino change flavor. I'm just going to briefly talk about how this fits into our bigger picture that I talked about last time. So if the electron neutrino is like this in the sun, it has a very small nu1 component and a very high probability of being a nu2. and then we observe 1/3 on Earth, then we can infer that the nu2 state is about 1/3 electron neutrino. And this fits into our bigger picture of oscillations that I showed last time, where I outlined the different mass states and the different flavor components of how they relate to each other. So what the solar neutrino is doing is filling in this piece of the puzzle. It's telling us that the nu2 state has about 1/3 electron component. And then we have to resolve this with all of our other terrestrial oscillation experiments to build up these other pictures that we talked about last time. So that's how solar neutrinos, that's how we can think about solar neutrino oscillations. Now, I want to talk about other things you can do with solar neutrinos. So we actually have a host of solar neutrino detectors in this day and age. So I've already talked about the chemical experiments. That was the homestake experiment shown up here. There was another one done, similar concept, but using gallium as the target, but also looking at a chemical reaction induced by neutrinos. Then we have water Shreinkov detectors. These are giant detectors filled with water where the neutrino interacts and produces Shreinkov radiation that you then detect to infer something about the direction or the energy of the neutrino. Next, you have liquid scintillator detectors. These detectors have a scintillator material inside so that when a neutrino interacts, you collect a lot of light from them. And that light gives you a very good measurement of the neutrino's energy. And then something new that we first did last year is detected solar neutrinos using a new type of detector called a noble liquid detector. And I say new, these detectors have been around for a long time, but their first application to neutrinos was last year. So very exciting. So in lecture 2, I talked about the Borexino detector, but I didn't really go into too much details about the things we've learned from it. So just as a reminder, the Borexino experiment is, you can think about it like an onion. It's got liquid scintillator at the center, and that's the main thing that you look for neutrino interactions in. But that onion is just part of the whole detector because what's really important for solar neutrino experiments is to reduce the background, so reduce the other kinds of things that could get in and fake the signal of a solar neutrino. So the liquid scintillator is contained within a nylon vessel, but then that whole vessel is surrounded by a buffer liquid, mineral oil, to stop radiogenic or radioactive material from entering. And then that whole buffer liquid is surrounded by water to suppress neutrons from entering the tank or to allow the researchers to identify cosmic muons that might pass through the detector that aren't due to solar neutrinos. So the result of all this effort is that Borexino became one of the cleanest detectors we've ever built. So very low background, and it applied its low background capabilities to measuring solar neutrinos very precisely. So the first thing I want to talk about, our measurement that Borexino did, is luminosity from using neutrinos. So the idea here is that in the core, where there are fusion processes, those processes are producing a lot of photons. As those photons are emitted from the fusion processes, they make their way out of the core, but the matter is so dense that those photons are absorbed and re-emitted over and over again, so that the photons from the core actually take, or the energy from the photons in the core actually takes thousands of years to propagate its way all the way to the surface. So another way to think about that is if there's a change in some fusion process in the core, we wouldn't know about it for thousands of years because the light that we're seeing from the sun was emitted from a process in the core thousands and thousands of years ago. But this is not true for neutrinos. So neutrinos that are produced in the core, they just travel straight out, and we observe them within 8 minutes of their production on Earth. So you can think about neutrinos as kind of a real-time probe of the sun's core, whereas photons from the sun are not. We don't get a real-time measurement of the solar physics from the photons. So Borexino did a measurement where they looked at the solar neutrino rate, and they compared what they would get, or what they would predict the luminosity from the sun as based on the solar neutrino rate, and they compared it with what we observe from the sun using photons. So the measurement result is down here. You can see that based on the size of the plus or minus over here, that the measurement from Borexino was a lot less precise than what we get from the sun, but the numbers agree very well with each other. So what this is saying is that our sun is very stable over thousands and thousands of years because the signal from the light matches the signature from the neutrinos. So that's one interesting thing you can do. Let's go back to Beta's CNO cycle. So this is another picture of that cycle with a little bit more detail. So I mentioned that as you go around the cycle, you're changing elements into different elements through fusion reactions. So starting with carbon-12, gaining a proton here and emitting a photon losing or converting a proton into a neutron at this stage and emitting a neutrino. So as you go along the cycle, you're doing these fusion processes and decay processes, and you're producing neutrinos in each one. And then at the end of the day, you get some helium, or you essentially just converted some protons into helium, and you start back with the same carbon-12 that you had at the beginning. So this cycle, there's no way to detect it with light, it turns out. The only way to detect it is to see if there are any neutrinos that come from this cycle that we can see on Earth. And so Borexino did this measurement in 2020. What you can see on this plot here is the energy that they measured in their detector, and then their data in these black points. And what they're looking for is to try to build up a spectrum that adds up, that accounts for each different component that they can measure. So most of the components here are actually different types of solar neutrinos or radioactive backgrounds. So for example, this 210 bismuth line here, this is a radioactive background that even though they're a very clean detector, they still have some component of it. So they're competing with different things, but what they found was that if they put 0 in for the CNO neutrino flux, then it was a bad fit to their data, essentially. They had to include some component of the CNO neutrino flux in order to explain their data. So this was very strong evidence that our sun indeed has a CNO cycle. And based on the measurement of the flux from Borexino, we can conclude that our sun produces about 1% of its energy through this cycle. And this is a really cool measurement because we have not, or we don't have evidence for the cycle before. So yeah, it helps with playing into developing models of stellar evolution, how stars form. Based on the metal content that we can observe in our sun, we can then infer to other stars about how they get their energy. Last thing about solar neutrinos, I want to talk about these nuclear recoils that were just detected in 2024. So one thing that a neutrino can do that we don't talk about very frequently for good reason, but a neutrino can interact coherently with a nucleus. And what I mean by that is that the neutrino, instead of scattering off of a proton or a neutron within a nucleus or an electron, it scatters off the whole nucleus at once. And so that whole nucleus has some recoil coherently. So the reason we don't talk about this reaction very often is because it's very hard to see. So even though neutrinos can do this a lot, the nuclear recoil is only, or the nucleus in the recoil is only moving with about a keV of energy. So that's about thousands of times less than what we observe in a neutrino experiment, a typical solar neutrino experiment. So it's too low to be spotted by most neutrino detectors. So for a long time, we kind of ignored this as a process. It wasn't a very viable way to see neutrinos. But it turns out that over the last couple decades, dark matter experiments have been getting really good at building very sensitive detectors. Now, dark matter detectors are a lot smaller, and it's kind of a topic for a different lecture series. But the way dark matter detectors work is basically by looking at very small amounts of energy deposited in them, and then they have a detector that reads out the signal from two different processes. So first, you can imagine a neutrino interacting and giving a little bit of a kick to this nucleus. It then produces a cloud of electrons and also some light. That light arrives at the detector very promptly at the top and bottom of this detector. You can imagine that there are light readout sensors here. And so what you measure is the charge here. Then you can apply an electric field and drift those electrons up, and you get a second signal. And what's nice about this is that based on the position of these, of the light that's detected and then the time difference between the two pulses, you can calculate where in the detector the event happened. Now, to give you a sense of scale, this kind of experiment is about 100 times smaller than a typical neutrino experiment. So again, not really something that you could imagine using for solar neutrino detection. But actually last year in 2024, the Xenon 1-ton or N-ton collaboration published a measurement where they observed these very low energy nuclear recoils due to solar neutrinos, and they made a measurement of the solar neutrino flux for the first time in this kind of detector. And it agreed with a typical solar neutrino experiment like the SNO detector. So their measurement is not as precise, but it's the first time this has ever been done, and the detector is only 100th of the size of the SNO detector for comparison. Okay, so that's all I want to say about solar neutrinos. Next, I want to talk about neutrinos from within our galaxy. And the story starts with a star kind of at the end of its life. As the fusion processes in the star come to an end, what happens is an iron core starts to form in the center of the sun. So the fusion processes run out of hydrogen fuel, and they start fusing together heavier and heavier elements. What happens as this process proceeds is that the iron core gets bigger and bigger as the fuel keeps running out. And if we zoom in a little bit, then at the very center of the core, what's happening is that there's a competition going on between gravity pressing in on that core and pressure of that core pushing outward against the gravity. So what is this pressure? So we have to go back to our friend Pauli, who proposed the neutrino. He also did this other thing, which you might have heard about, called the exclusion principle. So the exclusion principle says that electrons, that identical electrons can't be in the same atomic orbital in matter. And so in this picture where I'm showing a helium nucleus and has 2 electrons, this orbital is filled up. There can't be any more electrons in there. And the reason has to do with quantum mechanics, in particular a quantity called spin, which we'll revisit in a future lecture, comes into play. But the idea here is that as you add more and more pressure, pressure to atomic nuclei, those energy levels start to fill up, and the electrons become more and more energetic. And that creates a pressure that pushes outward against the force of gravity here. But then what happens next is, thanks to another friend here, so Chandra Sekhar, who was a UChicago faculty here for a long time, took Pauli's idea and then decided to calculate what would happen. Is there some kind of maximum where gravity actually wins out against this electron pressure from Pauli? And what he developed was called the Chandra Sekhar limit. So it's a number where it says if the star is too massive, then gravity wins out over electron pressure. If it's not massive enough, though, the star just becomes a white dwarf, where the electron pressure holds it together, but gravity is no longer in competition with it. And these white dwarf stars, here's an example of one. This is the Sirius A star, and then the Sirius B star is a white dwarf. And you can see it's very dim compared to its companion, Sirius A. But what happens if you exceed the Chandra Sekhar limit? Well, here's a picture of a galaxy. And if you exceed the Chandra Sekhar limit, then it's hard to miss. So in particular, this is a picture of the galaxy imaged with a bright supernova shown there. So there are big consequences for exceeding the Chandra Sekhar limit. So this was a supernova 1994D. It's a type 1A supernova. There are other types of supernova, and in particular, the ones that we're going to talk about are core collapse supernova. But the mechanism for triggering the supernova is very similar. Okay, so supernova neutrinos. So back to this iron core picture. So we've now exceeded the Chandra Sekhar limit. So we're now, gravity has now won out against this electron pressure. So what happens next is that these electrons combine with the protons in the nuclei and produce neutrons and electron neutrinos. So the amount of neutrons in the star's core is building up. What happens is that you're starting to form what we call a neutron star, where the material in the core is essentially being converted into pure neutrons. So it's an incredibly dense material, and you're emitting neutrinos in this process. The neutrons that are on the outside of the core are also undergoing beta decay, just like we see in other neutrino experiments. So there's also neutrino emission there. So in particular, you have both electron neutrinos, anti-electron neutrinos. It turns out you get neutrinos of all flavors through these processes. So then zooming out back to our star, we still have this matter that's infalling. We've now exceeded the Chandra Sekhar limit, so there's been a release of pressure, but we now have this neutron star core that is incompressible. It can't be decreased in size at all. So the material is coming in, and also the density. Let's see. Yeah. So the material is coming in. The density is so great that the neutrinos are actually trapped inside. So even though the neutrinos interact very weakly, the density is orders and orders of magnitude higher than it is in the sun, and not even the neutrinos can escape at this point. But as the matter starts to come in, it actually hits that neutron star core and then rebounds. And now you have matter passing, or the matter rebounding from the core, passing matter that's still infalling, and you get a buildup of friction. that friction produces heat, produces light, and also produces neutrinos. So what happens next is kind of unclear. We don't have a very good model of it, but at some point, the neutrinos are freed. The density gets low enough where the neutrinos can actually escape and free stream. And that process lasts about 10 seconds. And then following that, there's a big burst. So the shock wave of the supernova happens. So I'll tell a little story. So if you were a graduate student working in Japan on February 23rd, 1987, your office might have looked something like this. So you have a nice little teletype computer over here, and you're working with some electronics. This was the case for a couple graduate students working on the Kamiokande experiment back in 1987. They had nothing to do with neutrinos at this point. They were really just they're looking for a process called proton decay, and they never found it. But it turns out that it was very fortunate to be on this experiment on this day. And it was even more fortunate because these graduate students went on to do some very cool things. So in this picture, it's actually Nobel laureate Takaki Kajita and Masayuki Nakahara, who were on shift on the Kamioka detector on this day. So what happened next was there was a historic fax sent. So in 1987, on February 26th, a fax was sent to the University of Pennsylvania Department of Physics. Sensational news, a supernova went off just a couple days ago in the Large Magellanic Cloud, about 50 kiloparsecs away. This is what we've been waiting for 350 years. So a statement that reflects that these supernova events are quite rare, and the previous one that had been detected was in the 1600s. The previous one that was this close. So those graduate students went back and looked at their data from their Kamiokande experiment, and what they saw was this. So this is a readout of the trigger rate of the experiment. So what I'm showing here, okay. Yeah, so this is the detector activity as it goes along, and this is just noise. And then all of a sudden, you get a lot of events all at once, and then you go back to noise. So zooming in on this region a little bit, this is kind of what it looked like zoomed in. So in terms of seconds, all this activity we can attribute to neutrinos from a supernova reaching Earth. So this is a 600-second window around that time on February 23rd, 1987. So they went back and they looked in their data and they saw that they had neutrinos. So what does this look like in Kamiokande? So Kamiokande is a water Cherenkov detector. So as the neutrinos interact, they produce Cherenkov light, and that Cherenkov light travels to the walls of the detector, which are instrumented with photon detection units called photomultiplier tubes. And that Cherenkov light, as it propagates outward, it creates these rings in the detector. So what they saw in 1987 was a lot of these rings appearing all at once in their detector within a 10-second window. The Kamiokande experiment was headed by Masatoshi Koshiba, who also won the Nobel Prize in 2002 for pioneering contributions to astrophysical neutrino detection. Okay, so actually Kamiokande was not the only experiment that was online in 1987. So there were 3 experiments. We had Kamiokande in Japan, IMB here in the United States, and then the Baksan Underground Simulation Telescope, or BUST, in Baksan, Russia. And these 3 experiments comprise the world's neutrino data, or supernova neutrino data to date. So this is all we have. We have the energies of the neutrinos, and we have the time that they arrived. And you can actually see quite a nice pattern here, so that as the supernova evolved, you got neutrinos, a lot of neutrinos early on, with varying energies, and then as time went on, the energies kind of decreased, and the neutrino emission kind of became more faint. This data is very cool. And within 10 seconds, we learned quite a bit of things about supernovas and neutrinos. So the first thing we learned was that about 99% of the energy released in a supernova explosion is from neutrinos. This is just based on the neutrino flux that we observed on Earth compared to the luminosity of the supernova. We also learned something about the neutrino mass. So based on the arrival time of these neutrinos relative to when the supernova detonated, you can calculate how fast the neutrinos were moving. And we found that based on this, that they arrived essentially at the speed of light, that their mass has to have a lower bound, an upper bound. It can't be heavier than 15 electron volts, otherwise they would have been too slow to reach the Earth when they did. And then finally, this was a test that neutrinos are stable over light-year distances. So in other words, we didn't have some kind of unexpected fall off of neutrinos or missing neutrinos from this process. It agreed with what we expected. So the supernova 1987A is the name of the supernova, and we're actually still learning about it. So here are 3 images of that supernova remnant. So the first one taken in 1987, this is basically when it was at its peak brightness by an observatory here. Then we made better telescopes. So in particular, Hubble imaged the supernova, and you could see the supernova remnant at the core there with the ejected matter in these different rings. And then finally, recently we have the James Webb Telescope has also revisited the supernova and taken some really beautiful images of the supernova remnant. So this is a composite image showing the light from different wavelengths with different colors superimposed. There's also was a recent evidence that the supernova remnant is actually a neutron star. So the way this was done was using the James Webb Telescope, looking at in different wavelengths, again, looking for different types of gas that would have been ionized based on the radiation emitted from the neutron star. So another interesting study, but a little bit outside the scope of this talk. So what we're doing right now is preparing for the next supernova. So again, so they were waiting 350 years between the previous supernova and the one in 1987. We actually think we're a little bit more optimistic about the rate, so we think that there should be about 1 to 3 per century, and the estimates vary, but it's about that many. So it could happen any day. We're kind of overdue in some sense for a supernova. And so what we want to do with the next supernova is just be ready and have a good way of learning everything we can about it. So there are a couple things that we want to or be able to leverage for the next supernova. So the first one is that we have a lot more neutrino detectors online today than we did in 1987. So that means we can look at neutrinos from the supernova in different energies of neutrinos and different flavors. We also have much larger detectors than the Kamiokande and IMB and Boxon detectors. So we expect instead of 13 events, we'll have 1,000 events, let's say, for the next supernova. And then we also have a lot of multi-messenger follow-up opportunities, which means we can look at that supernova not just in neutrinos, we can also look at it in light, in X-ray, in telescopes, and also in gravitational waves. As of 2017, we now have gravitational wave detectors. So the next supernova should be just a very rich event that will provide us a lot of science very quickly. So the other thing I want to talk about is what we can do with neutrino detectors, which is something called neutrino early warning. So thinking back to that picture I showed of the supernova, where the neutrinos were all trapped and then they escaped right before the burst, this is actually a measurable effect. So the neutrinos from a supernova actually get a head start when they're emitted from the supernova explosion. And that head start can be up to a couple hours. Which is really cool because the neutrinos are traveling at just about the speed of light, and so the light from the supernova is trailing behind it. The supernova neutrinos actually reach Earth before the light does, even though they're both traveling at the speed of light. And from 1987A, by looking back at the data, we found that the neutrinos arrived about 3 hours before the supernova. So even though we didn't detect the supernova with neutrinos first, we now know that using neutrino detectors, we can actually get a head start or say that a supernova is happening somewhere close by, and then point out to the astronomer community where the neutrino is happening, or to get ready to move your telescopes over to look at it. So the program for this is called SNOOSE. It's the Supernova Early Warning System. And it's basically this network worldwide of neutrino detectors coordinating with amateur astronomers and different observatories to coordinate a follow-up. And so here's just a map of some of the the astronomers and plus neutrino detectors, and then also where we'll have future neutrino detectors shown in green here. So there are a lot of detectors that are participating in this. So we have Super K over here, the SNO detector, these liquid noble detectors that I talked about here for solar neutrinos, oscillation experiments like NOVA that I talked about last week, IceCube, one of these big Antarctic detectors, and then some other ones that are just turning online now, like this one here is Juno. It's a liquid scintillator detector we'll talk about later. Okay, so then we're actually very optimistic for supernova. So this is a list of potential supernova candidates. And they're all pretty close. So the units here are kiloparsecs, which in terms of light years is, let's see, so Betelgeuse is this one, Alpha Ori, 0.22, so that's about 700 light years. So Betelgeuse up here, this is part of the Orion constellation like I'm showing here. It's the shoulder, and it's a red supergiant. So we think it's in its last stage of its life. There was some excitement over Betelgeuse. There was the great dimming of Betelgeuse, which we actually don't really have a model of how that great dimming relates to its chance of a supernova, but I pulled one quote from an article about the dimming of Betelgeuse where a scientist was quoted as saying, "It will go supernova sometime in the next 100,000 years." So, I mean, put it on your calendar, right? I mean, okay, so I want to talk about supernova in a modern detector like Super Kamiokande. So this is an evolution of the Kamiokande experiment where the detector was scaled up by 50 times. So 50 kilotons of water up from 1 kiloton of water. So even at 10 kiloparsecs, which is about 30,000 light years, the detector would capture thousands of events. And if you looked at the direction of those Shrentkov rings on the sky, you would see this, just a tons and tons of events. And coming from all directions, because when the neutrinos interact from the supernova, there's no preferred direction for anti-electron neutrinos. They capture in an inverse beta decay process, and that positron signal that creates the Shrentkov ring that is being measured by Super K can come out in any direction. So it's kind of a mess, but yeah, it would just be, this picture is just to illustrate that it would be thousands and thousands of events. There's one other trick, though, which is that you don't really have to wait because supernovae have been going off throughout the entire cosmic history of the universe. And so what we expect, actually, is that our universe is filled with neutrinos from past supernova. And we call this the diffuse supernova neutrino background, or DSNB. The problem with detecting neutrinos from the DSNB is that the universe is constantly expanding. And so there's this effect called cosmic redshift, where things that are far away from us are getting further, are accelerating away from us at faster and faster speeds. And the effect that has on the neutrinos is it shifts all of their energy down to lower energies, making this signal kind of hard to detect. Fortunately, we have some really clever experimentalists who realized that you could, with a large enough detector, still maybe see some of these, depending on the model. So the Super K gadolinium project, also known as Super K GD, is an effort to upgrade Super K to be sensitive to these diffuse supernova neutrino background neutrinos. And the idea here is that in supernova explosions, you'll have anti-electron neutrinos, which can undergo a process called inverse beta decay that I mentioned before, where you have an anti-electron neutrino interacting with a proton, creating a positron and a neutron. And the trick here is that if you can tag this neutron and this positron, then you can be very confident that it's an inverse beta decay event, and you can reject a lot of backgrounds that make this search for the diffuse supernova neutrino background complicated. So a lot of experiments that I've talked about already, so in particular the reactor neutrino experiments, have used this, but they're too small to see the diffuse supernova neutrino background. Really, Super K is our kind of best experiment to do this in. The trouble is that Super K can't see the neutron very well. So in water, the capture rate of a neutron in water is only about 20%. So you miss about 80% of events that are inverse beta decay just because it's a low efficiency of capturing that neutron. The idea behind the SKGD, though, is to replace some of the protons in the water with a much heavier nucleus, gadolinium. In particular, because it has a very high neutron capture cross-section. So the idea here is that you put in a little bit of gadolinium to really improve your rate of capturing these neutrons so that you can then tag a lot more efficiently these inverse beta decay events and hope to see a signal from this DSNB. So the only trouble is that to put a little bit of gadolinium into Super K, you need a lot. So Super K is 50 kilotons. 0.1% of gadolinium in Super K is about 10 tons, and it comes in the form of salt, so gadolinium sulfate. So this is a picture of Super K. You have to put 0.1% of gadolinium into it. That's about 10 tons of material. So fortunately, this was done. So these are some pictures of the gadolinium being stacked up in the Super K mine. It comes in these bags that have been radioassayed to make sure the gadolinium is pure and not emitting any radiation of its own. And it was done in 2 stages. So the first shipment of gadolinium arrived in 2020. There were about 13 tons of it. And it comes in this gadolinium sulfate. By mass, it's about 0.01% loading of gadolinium. 2022, a next loading was done where they doubled the amount that was added, and that bumped up the concentration of gadolinium to 0.03%. So this is also a picture of what it looks like putting the gadolinium into the water system of Super K. So it comes in these bags. The bags it looks like salt. They go into this water system here, this hopper, that then takes the gadolinium and pumps it into the tank. And then that gadolinium recirculates around and dissolves in the water. So this is the idea. So Super K has been taking data with this gadolinium for a couple of years now, and they recently published an analysis of the first couple of years of gadolinium data here, looking for this diffuse supernova neutrino background. So what you're seeing here is an energy spectrum of the events that look like inverse beta decay events in Super K. And the color boxes are showing the background contributions. So mostly from low energy atmospheric neutrinos, and also some cosmic rays which enter the detector and produce radioactive junk, essentially. That's the spallation in green here. The prediction for the diffuse supernova neutrino background is shown in red. And you can see that there's a tiny, tiny, tiny excess just right where you expect that signal to be. So is it a hint of the diffuse supernova neutrino background? It's too early to tell. This is still 2 events in this bin over a prediction of 1 event. So not very convincing, but it's possible that we'll see another signal, or we'll see a signal in the next few years. So one other thing that you get with gadolinium is supernova direction. So I mentioned, or I showed this plot before, that with a 10 kiloparsec supernova, you would have thousands of events in your detector. This is actually all events, though. And if you have very efficient tagging of these inverse beta decay events that are producing electron rings with random directions, essentially, if you then have gadolinium that can efficiently tag them and filter them out, then what's left are just the events where the supernova neutrino scatters with an electron, and that actually does have some direction correlation with the supernova. So now if you look at the events in your detector on a sky map, you can see clearly that there is a hot spot in the sky. So with gadolinium, we hope that Super K can be used to point back to the supernova and not just give astronomers a warning that, hey, a supernova is going to happen sometime in the next few hours, but some confidence about where in the sky they should point the telescopes so that they can be ready to look for it. Okay, so for the last few minutes, I just want to talk about neutrinos from beyond our galaxy. And the story here starts with this picture, which is pretty cool. But what it's showing here is a high-energy particle interacting in the atmosphere and producing a particle shower on Earth. So we call these cosmic rays. Cosmic rays are either a charged particle like a proton or a heavy atomic nucleus, and they have huge energies, and when they hit the atmosphere, they produce these giant particle showers that span kilometers across the ground of the Earth. And we've built experiments that kind of detect these cosmic rays, or the particles that are produced from these cosmic rays, so we can say something about their energy, but the origin is kind of a mystery. So actually, Fermi was one of the first people to propose a theory for these cosmic rays. So Fermi's idea was this process called Fermi acceleration, where if you had a charged particle moving around in space and there were lots of magnetic fields and moving debris around, then the particles that were in those magnetic fields would be accelerated back and forth across what we call a shock front. So the idea here is that there's some accelerating material, the particle is being carried along with it, it's moving in random directions, but as it's passing back and forth across that shock front, it's being trapped in a potential that's causing it to accelerate back and forth. So the only issue with Fermi's theory was that at the time they didn't really know what would cause giant magnetic fields or large shock fronts required to accelerate these cosmic rays up to the energies that we observe on Earth. But since Fermi's idea, we now know that there are really exciting and energetic places in the universe that actually have these properties. So this is an image of Centaurus A, which is what we call an active galactic nuclei. So it's a supermassive black hole, just like at the center of the Milky Way, but unlike ours, it's accreting matter. So it's pulling matter in and then spewing it out in different directions. And what you can see here are these jets that come out of the center of the galaxy. These actually go hundreds or thousands of light years in either direction.
up to a million light years in, depending on the kind of radiation you're looking at. So again, this is another composite image of optical plus X-ray plus microwave images that are stacked together to show the different components of this. But anyway, these active galactic nuclei provide these extreme conditions that make Fermi acceleration possible. So in addition to Fermi acceleration producing very high energy cosmic rays, of course you can also get neutrinos as these very highly accelerated particles smash into the dust or the radiation that's also being thrown around in these extreme environments. So the experiment I want to talk about next is IceCube, which is an experiment at the South Pole that is looking for neutrinos from these astrophysical sources. So the way IceCube works, it's got a central station here on the top of at the South Pole, and then that sits in the middle of a large array of different strings that are drilled into the ice and then deployed about 14 or 1,500 meters below the surface of the ice. And each one of these strings has a collection of optical modules attached to it, so that as a particle comes through the ice, you can see the light from that particle. And this works because the particles, or the neutrinos that IceCube is looking for, are so high energy that the particles they produce will travel kilometers of distance through the ice. So you don't need to have have these strings very densely packed together. So here's a top view of the IceCube layout. So again, the station sits here, kind of in the center. And there's also an extra cluster of strings with these optical sensors on them that are closely packed to look at low energy neutrinos, or lower energy neutrinos. I just want to point out one interesting thing about this diagram, which is the string 47 here. It's kind of off grid with the other ones. And I asked some IceCube people why this is. And the best thing that they gave me is a reference to somebody's thesis, where in a footnote, they refer to string 47 as the pork chop string. And the reason is, claimed by this thesis, that at the original location where they wanted to drill the hole, they struck a crate filled with pork chops that they think was flown in by another Antarctic expedition. And then they couldn't drill at that site anymore. So they had to move the drill over to miss the crate of pork chops. So slightly off-grid, but otherwise very regular. So, okay, so what do events look like in IceCube? So I have two pictures here. The one on your left is the track event, so where the neutrino interacts and produces a muon. And that muon, with as much energy as produced by these active galactic nuclei, travels for kilometers along through the IceCube detector. So what you're seeing in this picture here are the strings lit up with the charges, and the color scale shows the time. So these red ones have arrived early, and then these ones have arrived late. So you can tell the direction of the muon traveling through the detector based on the timing. So these are mostly produced by muon neutrino interactions, but then you can also have particle showers where the neutrino, if it's an electron flavored neutrino, will interact and just the electron won't travel very far. So what you get is all the charge kind of deposited close to the center of the interaction, and it looks like this. So you can tell kind of the flavor of the neutrinos based on the pattern of hits that you observe in IceCube. So here's another view of a IceCube track event, and this one is particularly special because what they found was that it was coincident with activity from a blazar, so an active galactic nuclei that had a flare in gamma rays at the same time as this event was detected. So this was pretty direct evidence that these blazars are sources of high energy neutrinos. Okay, one other thing you can do with IceCube is look into our own galaxy. So this is a picture of the galactic plane viewed from different wavelengths. And as of a couple of years ago, we can add neutrinos to this picture. So the top one is showing the visible wavelength, which is our galaxy that we're all familiar with. If you then do the same thing with a gamma ray telescope, you can also look past the kind of dust and debris in the Milky Way and see that there's hot spots in the sky due to gamma ray sources. We think that neutrinos are associated with these gamma ray sources, so the expectation is that where there are gamma ray sources, you should also see neutrinos, just like the blazar. So IceCube put out this map down here of the neutrinos in the sky, and these hotspots are showing that there is some correlation between the gamma ray sources observed. So we really now have kind of a multi-wavelength view of the Milky Way, including neutrinos with this technique. I'll say that this technique could be improved a lot. So one disadvantage of IceCube is that being at the South Pole, the plane of the galaxy is kind of in the sky that's directly overhead, where they have a lot of background. It's easier for them to look below in the northern sky, actually, because then the Earth shields from a lot of background radiation. So if we had another experiment in the northern hemisphere that made the same measurement, they would be able to, or they would be shielded from a lot of background and could make a more precise measurement. But it's still very, very cool that IceCube was able to do this. Okay, so I just want to end with a couple of thoughts about what else could be out there. And well, we know one thing that's out there, which is the cosmic microwave background. So this is radiation left over from the Big Bang that permeates the universe. And the average temperature of this radiation is 2.7 Kelvin, so very close to absolute zero. But this actually has some implications for our cosmic ray picture. So if we imagine these high energy cosmic rays traveling through the universe in the sea of background radiation, then what can happen sometimes is that these cosmic rays can interact with that background radiation and produce charged particles like pions that can then decay into neutrinos. And we call the neutrinos that are produced from this process cosmogenic neutrinos. And what's interesting about these is that we think that these cosmogenic neutrinos would be the highest energy thing we could observe on Earth. And the reason for that is that the cosmic rays that are produced in these particle accelerators are these active galactic nuclei, let's say, these astrophysical particle accelerators, won't make it to Earth in most cases. The reason is because as they interact with the cosmic microwave background, they lose energy. But the neutrinos that are produced in the first interaction, let's say, of a cosmic ray with the background radiation will just travel to Earth and they won't interact a second time. The neutrinos won't interact a second time. So the picture here is showing just a spectrum of the cosmic rays and neutrinos that can come from these extragalactic sources as a function of the energy. And this dashed line is showing the production of the cosmic ray at the source. And then the solid line in black is showing the cosmic rays that actually reach us. And so you can see, due to these interactions with the cosmic microwave background, the cosmic rays that are produced lose energy as they travel to Earth, so they tail off. But the neutrinos that are produced in these interactions of the cosmic ray with the cosmic microwave background don't. So actually on Earth, we expect to see the highest energy things that we could possibly see would be neutrinos. We have one detector online that has possibly seen one of these cosmogenic neutrinos. So this is the KM3 net detector, which started taking data in 2021. The way it works is very similar to IceCube. So it has these strings of photosensors, but this time, instead of being drilled into the ice, they're anchored to the bottom of the Mediterranean Sea. And as charged particles travel through the water, they produce light that is then detected by these strings. So if you have a very high energetic neutrino interaction nearby, it could send charged particles through the detector that produce a lot of light that you could then see and reconstruct that event. So this is an animation showing the highest energy neutrino ever observed. I mentioned this at the beginning of the first lecture, so here's a little bit more detail about it. This is the detector is located just off to the side, or very close to Sicily here, and this is an animation showing a neutrino interacting and producing a charged muon that then travels to the detector and lights up basically every photosensor on this experiment, just because of the energies involved. So what they estimated was that the muon had an energy of about 120 PeV, and that corresponds to a median neutrino energy of about 220 PeV, or 10,000 times the energies that we can make at the Large Hadron Collider. So a really, truly high energy event. So KM3net did some follow-up studies to try to identify the possible origin of this. So there were two papers released. One looked at whether it was possible that this event came from blazars, like the active galactic nuclei scenario, and the other one was if it came from a cosmogenic source. So this plot shows the KM3net event at the center, and then different blazar candidates in the sky that were kind of in the vicinity of it. And what they concluded was that there was really no clear match. So there were some blazars that had some activity at the same time, just like the event that we saw with IceCube, but they're kind of on the fringes of where the event was coming from. So it's not very likely that it came from these. The ones in the center were less favorable, so maybe they've only been observed in one wavelength, but they're not really convincing sources of a lot of activity. So still unknown for that case. For the cosmogenic case, it's actually a more complicated picture, which is that if the neutrino was actually of cosmogenic origin, then the question becomes, why haven't we seen this from other experiments? So we can measure the cosmic ray flux on Earth, and that should infer what we can learn, or should imply something about the neutrino spectrum. But there's some tension there. Basically, we haven't observed cosmic rays with high enough energy that would imply that there should be a component of the cosmogenic neutrino flux with such a high rate that KM3net could see it. And then there's also the IceCube detector itself, which is a bigger detector, and it also has been taking data for over 10 years, which has not seen anything this energetic. So really, we truly don't know where this event has come from. There's no clear picture. We just have to keep taking more data to see. So this last slide, I'm not really going to talk about. It's more of an advertisement that this is just scratching the surface of high-energy neutrino experiments that you can do. Last year, there was a great Compton lecture series by Christoph Welling, who talked about this in more detail. So I would encourage you to go to the Compton site, look at Christoph's talks if you want to know more. And I'll just end there. Neutrinos are a singularly unique probe of our universe. And by building detectors, or without building detectors, we're blind to them. So it's really exciting that we have neutrino detectors online. Thanks.